Hello, everyone. Come on in.
Hey, good evening, Professor. I had
Oh,
a quick question.
yes.
So I was confused about the due dates for the lab. So when I read the syllabus, it said that the labs were due every other Thursday, but then I was looking at the grading and it says that lab two is due this Thursday. So
Yes.
did when was lab number one due? Was it due Monday? Because
So
I
the way it works is you're supposed to have two labs a week during the summer. That's probably
and
what's
that was
screwing
the
up.
confusion. Okay, that was what.
So
Okay, that makes a lot of sense. Okay.
Tuesday lab is supposed to be due. It used to be before class at the following Tuesday, but now I just make it 11:59 on the following Tuesday, and then the Thursday lab is due at 11:59 p.m. the following Thursday.
Okay. Okay.
Uh,
So, all right,
Technically,
that
it's
clears up a bunch. And
yeah.
then do you know when the dates are going to be fixed?
I fixed them today. I did send out an email about repairing the dates on the tests and the schedule within the syllabus. That was all done today. I was just going to say though that the actual labs that we did this past week, they were supposed to be due today. But if you need more time, it's not a problem because I remember I screwed up a little bit. So if you need
Okay.
more time for this Tuesday or for this Thursday lab, just let me know. It's not a big deal. I'm not going to mark you late or anything for.
Okay. In order for me to get that time extension, do I need to send you like a formal email just so that we don't
No, you can just
forget?
turn it in. No, you can just turn it in whenever it is, and I'll automatically give you the extension.
Okay, I appreciate that. All right, Professor.
You're welcome. And that's for everybody, of course, not just for David, even though he's clearly kind and handle things nicely.
Absolutely. Yeah, you try not to bite the hand that feeds you. Everybody just trying to get better. You know what I mean? We just trying to get better. Thank
Yeah,
you, Professor.
you're welcome. Anybody else have any questions?
Yeah, I had a quick question. So for our exams, there's two exams for both the asynchronous course as well, right?
There's more than that. So the asynchronous class will have three face-to-face plus a final, and the three face-to-faces are all proctored and the finals proctored.
Okay. And then do we also have the online exam as well?
Yes, you get to take the online exams too, even though they're a much smaller proportion of the grade. But
Mm.
trust me, you'll be thankful because you'll feel so much more confident going into the face to face after you've taken one or two online tests first.
Okay. And also for the what's the difference between face-to-face exam and the one that's proctored like the final?
It just a difference in percentage. Like, if I remember correctly, what I did in the syllabus was the three face-to-face tests count as 25% total. So, like, each one's worth,
Mm.
a third of 25, and then
Mm.
the finals worth 30% all by itself. But I might have, I can't remember if I reversed those or not, but it's roughly that.
Okay. And so for the face-to-face exam, like does that mean that we're going into like TCC's like testing center to take that exam, or is it like online we might meet like a specific day to do that?
If you look at the syllabus, the way I made it for you guys for my asynchronous class is basically I say your test face-to-face test one is due by 6/3 or something like that. And
Mhm.
that means basically you'll have a week that ends on 6/3 for you to do it.
Okay.
So the
Okay.
dates are strictly from the syllabus, and I don't update them like I think it might have been Michael here asked me about. There's no due date for the face-to-face exam. I don't put the dates on there until they're actually visible and ready to show you. The date should be in the syllabus in the schedule, and that should be the correct dates for all the face-to-face tests and the online tests.
Okay. And for the face-to-face exam, are we coming into like a TCC testing center to take it, or?
Yes, that's the normal scenario. That's what most people do. So
Mhm.
you're able to do that at any of the TCC testing centers for no additional charge. But if you live somewhere where it doesn't allow you to just come to campus or come to a campus, then there's other ways, but those would involve you finding a proctor. having the proctor fill out the application to be a proctor, and then me approving the proctor, and then you possibly having to pay that proctor to administer your test.
Okay. All right. That makes
There's
sense.
also
Thank you.
some online services where they'll proctor it online with certain, you've got to have certain cameras and stuff like that. But that's another option you can do if you need it. But if you can't make it to the testing center for whatever problem, for whatever reason, make sure you try to find a proctor and talk to me if you don't know how to go about doing that.
Okay. All right. Sounds good. Thank you.
You're welcome. Anybody else?
For the proctor, do we have to get like an application from you?
Were you the one that emailed me about this? I didn't think Kaylee was the name. Uh,
Yeah.
it wasn't you. Okay. Someone
No, I know. I think it was me.
Wait, was you? Okay, go. Someone asked me about this. We normally, I normally just send it to the proctor once the proctor contacts me. Uh, so that's all you have to do. So, like, if you have someone that, for instance, is an acquaintance from a local school, or if you have a principal or a preacher or something that's willing to administer the test for you, they can apply. And all they do is you just send me an email and they say, "Hey, I've offered to proctor for such and such." And then I immediately send them an application. They fill that out, and it's done.
Okay, perfect. Thank you. And also for the first lab, there's no due date for the first lab. Do we turn that one in or is it just the second lab?
The first one's due. Technically, it was supposed to be due today at 11:59 p.m., but I've just told everybody because of the problems associated with me screwing up in the early part of the semester that if you need more time, it's no problem. You probably can turn it in as late as next Tuesday and not get points taken off.
Okay, and is there like a place to turn that in? Because there's no
Yeah, you
assignment.
can see that it should be if you look in the Canvas for this course, there's a week one module, and below that's a week one module for lab, and it should be in there. I'm looking at the modules right now.
For physics
Oh,
241.
basic. Are you in O2 or are you O01B?
I'm sorry.
Do you have me for lab or do you have someone else for lab? That
I'm O01B.
Okay, so you have me for lab. So yeah, that just means you're supposed to go into your O01B course and there'll be a week one. It says May 20th to 11:59 on May 26th, and it'll say see next module for this week's lab. And then down there below that, there'll be lab for week one. And that should have where you're turning stuff in. Do you not see that?
I see one for lab 2, but I don't see one for lab 1.
Okay, that might be something where I didn't, or I hit the publish button twice and thought I only hit it once. So it's there, but you can't see it. I'm going to pull it up right now and check real quick.
Okay, thank you.
Um, I had a couple people email me about that, and it was over the weekend. I think he texted me actually, and I corrected it first thing this morning, but I might have accidentally corrected it and then uncorrected it because I'm a goober. So let's see here. Helpful documents, that's there. And now I'm looking at week one. Yeah, that's there. It does say see below, see next module, lab one for week. Oh, yeah, it disappeared again. Yep. Okay. It's got the right date on it, or it had the right date on it, but I must have unpublished it. You should be able to see it now. Not only that, I don't know why it's not showing the lab one addendum either. That now it should be showing both the lab one addendum and
Okay,
lab
yeah.
one intro to lab. Do you see that?
Yeah, I see now. Thank you.
No problem. Sorry about that. I'm glad you called me on it because I definitely was under the impression that I had fixed that, which, like I said, I had, but it evidently I screwed up some other place.
And then I was just wondering for the test, do we have to take them a certain time of day or do we just take them whenever?
No, when we're doing the final exam, ideally the final exam and the face-to-face test, they would be ideal to take it at the same time. But what I have to do, since so many people are taking it at so many different times, is you'll have a slightly different version from each of your other students. Should be comparable in difficulty, but the order will be different. Some of the individual numbers will be different. But other than that, it's just you take it sometime during the week and know that it will be somewhat different from everybody else taking it at different times of the week.
Okay, so it's not like a certain day, it's just like whenever that week type of
Yeah,
thing.
for the N02B and for the O01B class, it's just I have a whole week interval for you to for you to complete it.
Okay, perfect. Thank you.
No problem. Anybody else?
Is it possible to repost the spring video?
Yes, that might have been something that got turned off as well. Beth also asked, and just to clarify, if we are entitled in enrolled in a different lab, we are not penalized. Yeah, you will not be penalized for not turning in the lab. If you're in N02B, you should not be in my lab unless something weird happened and we got that worked out for you. But yeah, you only have to turn in labs at one class. So whatever class you're enrolled in for lab, that's the one you turn in. All right, now I'm checking your videos. I'm looking at, are you in 241 N02B, the person that asked me for the spring video? Are
I'm
you?
in O1,
Oh, okay,
O01B.
that's cool. I want to make sure. Yes, you are. And let's see, lab for week one. Dang it, those two got turned off too. I actually had two of them and they both got turned off. I swear there's a gremlin in the system. But the videos are now there. There's one called short oscillation video and one called long oscillation video.
Thank you so much.
No problem. Sorry about that. Thanks for letting me know, though. I do appreciate it. That does happen sometimes. These buttons, between the buttons being slow to respond, my computer being slow to respond, and all that, I sometimes will hit a button and then get impatient and hit the button again and evidently turn it off again instead of turn it back on. So sorry about that. I'm still able to see the lab assignments in the Canvas course. Yes, if you're in a Canvas course that has a lab associated with it, then you're supposed to have that. But I think, Beth, you're saying that you're in my 242 N02B class, which doesn't have a lab associated with it. But sadly, when I got confused on which class it was linked to, I ported all the lab assignments into that Canvas. I will be taking them out, but you might see them from time to time. But you're not supposed to turn in if you have, Miss Raskovic or Dr. Johnson or whatever for lab. You don't turn anything to me for lab. Sorry about that, Beth, and I appreciate your your acceptance of my gooberness. Anybody else? All right, well, let's go ahead and get started. Last time I finished basically all that I felt was necessary, of course, for chapter one, and we're starting chapter two now. And chapter two is on basically one-dimensional motion. In fact, the chapter is called Describing Motion, Kinematics in One Dimension. So what we mean by that is in what we call mechanics, which is more or less what the first part of this course is. Physics 241 is essentially mechanics. It normally has a little bit of special relativity here at TCC, and then course two is thermodynamics and electrodynamics, and occasionally has some quantum mechanics. But mechanics is sort of basically what Newton gave us in his Principia. So the mechanics is involves two different things. It involves kinematics, which is the study of motion without necessarily knowing what causes motion, but knowing once the motion is detailed in a specific way, how far will the object go at a certain period of time? What will its velocity be at the end of that period of time? Or in what direction would it be if we're talking about two-dimensional or three-dimensional motion? But without respect to how do I actually make this thing have an acceleration, or how do I make it speed up or slow down or turn or something like that? When you're thinking about just how the motion plays out without wondering what made the motion, then you're doing kinematics. And then when you try to do the dynamics portion of mechanics, which is the other half, the dynamics portion is all about how do you make an object have a certain acceleration or a certain velocity at a certain time, that sort of thing. That involves us making use of forces or even potential energies and stuff like that. But the main thing is you can actually solve problems for the forces required to make an object have a certain acceleration or a certain velocity at a time later. And you're really just mostly concerned about how to make the forces work and how to analyze the effect that the forces have on the motion. So what we're doing now is that kinematics part, and largely a good fraction of it was done by Galileo after he had been sort of threatened with torture between him and the court system with regards to teaching that the sun is the center of the universe, which was a little bit problematic. But he had other problems that were going on as well. But anyways, he was brought up in a trial situation, showed the instruments by which he would be tortured, and he decided to recant and say that the sun is not the center and the earth is the center. But he was locked into in-house arrest and not killed, and that was probably a result of the then Pope, when this all finally happened, the Inquisition that convicted him and all that. When that happened, the Pope was fairly new, and in fact was a former cardinal that was pretty good friends with Galileo at the time. So we think that's more or less why he wasn't killed. But the good news is, he said because of the ruling, they didn't allow him to study and teach about astronomy, the universe, cosmology anymore. So he decided, given his information that he learned from copying someone's creation of the telescope, had led him to believe that he had a new system of the universe that had a heliocentric system. And in order to make sense of it, he needed to understand motion in general. So during his in-house arrest, he started discovering and detailing motion. So one thing he wanted to tackle was, what do objects do? He was going on Aristotle's teachings, which basically said there's 4/5 elements. The first four are earth, wind, fire, and water. The fifth being Mila Jovovich, but really just being supposed to be the quintessence, or the heavens. And the first four were basically responsible for the way things behave. So, for instance, things were made of either earth, wind, fire, or water, and they all had their natural place. The Earth's natural place is the center of the Earth. By this time, they did actually know the Earth was spherical. The wind was air, and air's place was above the Earth, as you can see in our atmosphere. And the fire was like the sun, and its place was up above the atmosphere. But the water would try to go as low as it possibly could, but not necessarily to the center of the Earth, but would still go lower. And then what also Aristotle had proposed was that all things fall at a rate directly proportional to their weight. So they had this idea that if something weighed 100 pounds and another thing weighed 10 pounds, then instantly when you let them go, they would immediately start traveling at this high velocity, in which case the 10-pound one would be 10 times slower than the 100-pound one. If it was 200 pounds compared to 10 pounds, then it'd be 200 times, or excuse me, 20 times faster for the 200-pound one. But again, it wasn't any acceleration, speeding up, or anything like that. Their picture was that it would immediately start falling with a rate proportional to its weight. Galileo said, I need to study that, specifically because he saw that there were satellites of Jupiter, and he had found them. In fact, we call them the Galilean moons. He called them the Medicean moons. But he found them, and he found that they weren't left behind, like the adage said, that people have used to assume that the Earth wasn't moving in ancient Greece, as well as in future places. Basically, the idea was that if a bird was sitting on a limb and saw a worm, if the Earth was actually moving, hundreds of miles per hour, as soon as the bird would lift off the tree limb, the Earth going several hundred miles per hour would take off and leave him in the dust. So that was the underlying understanding of how gravity and stuff like that worked, and physics in general worked, but it was wrong. It was dead wrong. And Galileo tried to discover exactly what was right, because he did see four moons that were not left behind like the bird. So he did it by allowing balls to roll down inclines. And what he learned is that when a ball rolls down an incline, it goes a different distance in each subsequent time interval, and in fact goes a farther distance in each subsequent time interval. So like in the first tenth of a second, it might go this far, but in the second tenth of a second, it might go that far, and the third tenth of a second, it might go that far, or something like that. But he also knew there was some limitations. When you drop a ball, it's hard to tell. Like you can't just look at a ball and see, does this actually speed up or is it just taking off at some fixed speed and going all the way down? So he said, well, I don't have the technology really to track down how these things are moving. So he chose to study an inclined plane specifically because the vertical component would be just like gravity, and the other component would tend to just make it go a little slower that he could see, so that he could see the motion. So that's why I was doing inclined planes and very gradual ones. And like I said, he found that one, he gave us our definition of constant speed. For instance, constant speed would be an object traveling such that it covers the same distance in the same unit of time. That unit of time could be anything. So for instance, you might take the unit of time to be 1 second. And if the car travels 3 meters in 1 second and it's a constant speed, then it'll travel 3 meters in the second, and 3 meters in the third second, and 3 meters in the 4 seconds. And that was his definition of constant speed, which is somewhat synonymous before you get to vectors with the word velocity. Uh, he also discovered, like I said, when you roll it down an incline, the speeds actually increase. And what they did was that interval of time, 1 second or whatever one you chose, if you chose that over and over again, you'd find that the ball rolling down an incline would go a larger distance with each subsequent one. That gave him an idea to make up what we now see as acceleration. He also found that when you rolled a ball up an incline, it tended to slow down. In other words, the distance traveled in a given amount of time got progressively smaller. And then he argued that if an inclined plane going down it causes it to speed up, and an inclined plane going up it causes it to slow down, it seemed reasonable that it would carry on with a fixed speed forever if the incline was neither up nor down. In other words, if you rolled it on a level surface, it should not speed up or slow down. And that was the first inklings of what we know of as Galileo's law of inertia, which would later be called Newton's first law of motion. So he basically said uh, objects tend to move at a constant speed in a constant direction unless acted upon by other forces. And he had to, basically say those forces, because what he discovered was when he was letting things roll down an incline, something else occurred. It would roll down an incline and then it would roll back up an incline, and it would try to reach, or it seemed to be trying to reach, the same height that it left from. And it was failing. So he said, well, I noticed it's skipping and sliding and skidding little spots and bumping up and down. So he went back and polished the track really, really good, the inclined planes really smoothly. And he found that after he did that, it came even closer to getting back to the same height. And eventually he said, okay, well, if I could imagine getting rid of all the random little forces that could be causing this thing to slow down, then ideally it appears that it would never speed up or slow down or change direction. It would just always move in a constant direction at a constant speed, covering the same distance for any given unit of time. And that's how we got a lot of the motion that we'll be studying now. So in order for us to do that, we need to first talk about section 2.1, which is reference frames and displacements. So I will tell you, let me go ahead and share my screen with you guys. So you might think that it would be good if we could just, focus on one particular reference frame and not have to have all these different coordinate systems and reference frames. And I get that. I get the desire to do that. But the problem is there's nothing in the universe that's sitting still. Okay. Uh, for instance, our Earth, and these numbers, I haven't done these calculations in a while, so I'm sort of going off my memory. They're good. There's a good chance that they'll be off even by a factor of 10 or 100 in some cases. But as a estimate, basically our planets around the sun are going on the orders of thousands of miles per hour, thousands, if not tens of thousands of miles per hour, just as a result of the Earth, for instance, orbiting the sun. It speeds up when it's closest to the sun and it slows down when it's furthest away, but it goes sort of roughly in that ballpark of 1,000 to 10,000 miles per hour all those times. Of course, changing directions constantly, but still, it does do that. Uh, if you then think about, well, what if we just took the coordinate system with respect to the sun? Because the sun's obviously sitting still. Well, it turns out the sun's moving pretty fast too. It moves on the order of 50,000 miles per hour to 100,000 miles per hour. And that's as a result of its orbiting around the center of our galaxy with a 250 million light year period. So it literally takes 250 million years for the Earth, Sun, Moon system to go from one point in our barred spiral galaxy to that same spot again. That speed is on the order of tens of thousands, 50,000 miles per hour. Then the galaxy, the Milky Way, is actually headed right towards the Andromeda galaxy, and the Andromeda galaxy headed right towards it on the orders of 50 to 100,000 miles per hour. So there's really is no really preferred coordinate system in which the velocity is zero. So we have to talk about relative coordinate systems. What I'm going to tell you is that there's a nice way of dealing with them. And the nice way I'm going to deal with them is this. I'm going to draw you a picture of what a, wait a second, all my pins are gone. I got to figure out where they went. Okay, that's not it. That's not it. Oh, there it is. All my pins are left. Okay. So when I say reference frames, what you can imagine is something like this. This would be an x-axis. This would be a y-axis. And by the right-hand rule, the z-axis would have to come out of the board. The positive z-axis would come out of the board. And this might be called system S. But there might be another system that has an x prime axis, a y prime axis, is called system S prime, and the velocity of S prime with respect to S would just be that V. And I put that little arrow over it. That's for those of you who've heard of vectors and know anything about vectors. Right now, we're just talking about motion that's in a single direction or possibly the opposite direction along a straight line like a rail or a track or something, because we're talking about one-dimensional motion here. So the one-dimensional motion can be truly in one dimension, or it could be along a wire, like a bead on a wire, and it can be quite curved, but still you'd have just one-dimensional motion because it's one-dimensional, meaning it can go right or it can go left, and that's all the directions it can go. Whereas if it's two-dimensional, it can go right, left, or up and down. So that's two-dimensional, at least the way we have it drawn now. So don't worry about that arrow thing. I'm just saying that's the velocity of the reference frame with respect to the old reference frame. So notice the wording, VSS, like this, means the velocity of S prime with respect to frame S. So that's what that terminology means. Later you'll see forces, and we'll do the same thing with them. We'll have two prefix or two suffixes, subscripts, if you will, and the subscripts will be the first one will be what's feeling the force, and the second one will be what's causing it. In this case, the first one is the thing that's moving, and the second one is the thing that you're measuring it with respect to. Now, once I have that terminology down pat, you could work out equations to relate all these things, but I'm going to tell you the main thing that matters right now is the addition of velocities. So let me show you what addition of velocities would be. And this sounds really abstract right now. I'm getting ready to give you a concrete example that I think will make it more sensible. So what I'm going to tell you is if you want to know the velocity of A as seen by C, then watch this. I'm going to explain, I'm going to write it out, and I'm going to leave spaces for subscripts, and then I'm going to fill in those subscripts so that you can understand why. So the way the formula works is right now we're calculating the velocity of A with respect to C. So this is like a ship that you might have labeled A. It could be a coordinate system that you labeled A, and then there's another coordinate system or another ship that you labeled C. And what we're asking for is what does object C think the velocity of object A is? That's another way of reading VAC. It's the velocity of A as seen by C, or velocity of A as with respect to C. So when I go to do this, what I know is the suffixes, or excuse me, the subscripts have to match the ones on the right-hand side, but in a weird way. So the A can be here, but I'm going to leave a space, and then I'm going to say plus, and then I'm going to put V. This time I'm going to leave a space and then put C. So what you see is this subscript corresponds to this one. This subscript, on the other hand, corresponds to the outer one. Okay. Now, if you have that, then all that has to be true is that these inner subscripts have to be the same. Oops, wrote it in the wrong spot. Okay. So these two outer subscript, or excuse me, these two inner subscripts have to be the same. So that is your addition of velocities formula. And what it says is the velocity of A as seen by C is the velocity of A as seen by B plus the velocity of B as seen by C. If you do this, even in 2 dimensions and 3 dimensions, when we start dealing with vectors, you will always get the right answer, assuming we were doing Galilean and Newtonian relativity as opposed to Einstein relativity. The only difference, by the way, is in Einstein's relativity, it would be the velocity of A as seen by C is equal to the velocity of A as seen by B plus the velocity of B as seen by C divided by 1 plus VAB VBC over C squared, where this C is the speed of light. So let me bring this home to you. So let's imagine you are riding on a flatbed Mack truck. So we're talking those big Mack trucks, like they carry, stuff back and forth to Target and warehouses and stuff like that, or Walmart. Now imagine one of those with just a flatbed, like they might put logs on, for instance, or something like that, or they might stack plywood on or something. So if you imagine a Mack truck riding down the road at 60 miles per hour, and you imagine you're on the back of that truck, on that flatbed truck, uh, ignoring air resistance and wind resistance, for starters, air resistance and wind resistance has a chance of blowing you off the thing by accident and making your throws get messed up again by accident. So you'd really like to ignore all that, even though it's always going to be an issue. But the main thing is, if you stood on the back of that flatbed trailer and the truck driver was driving straight north at 60 miles per hour, then your velocity would also be straight north at 60 miles per hour. But if you took a softball and did your, fast underhand pitch like Jenny Fitch or something, and you threw it at 60 miles per hour in the same direction as the truck is going, then someone that maybe is slightly higher than the top of the truck, maybe they're on a bridge that goes over the highway, they would look directly at this ball that's left your hand, is headed for just the top of the cab, say. Let's say she was actually throwing it from a little higher than the, let's say, the dashboard, so that her throw would just come off a little bit higher than the actual cab of the truck. If she threw it at 60 miles per hour and the truck was going 60 miles per hour in the same direction, I guess you all can tell me how fast the ball would be moving for that person on the little bridge that tries to measure it. Remember, the person on the bridge is sitting still, so it sees the truck coming at them at 60 miles per hour. What does it see the speed of the ball to be? Anyone? Anyone? Just like no one.
The same speed of the truck?
It would actually be twice the speed of the truck, because if you think about it this way, The truck is going to move a certain distance in, let's say, 1,000th of a second. And that distance is basically the same as 60 miles per hour multiplied by the time in seconds, which is, a thousandth of a second, say, but converted to hours. So you'll get this itty bitty distance. But during that period of time, that itty bitty distance is traveled by the truck. The ball that left her hand has also traveled that distance with respect to the spot on the truck directly below the ball. So that now, whatever that distance is, and obviously for 1,000th of a second at 60 miles per hour, it's not going to be a huge distance. But the neat thing is that distance that the ball moved over the trailer is exactly the same distance that the trailer moved over the ground. Therefore, the ball moved twice what the trailer did, and therefore the velocity of the truck being 60 more miles per hour means the velocity of the ball would be 60 plus 60 or 120 miles per hour. Does that make sense now that I explained it?
Yeah.
Okay. So if we talk about that, we can look at this particular example. So let's say truck example. The truck example, basically we have the velocity of the ball with respect to the ground, which is what we're looking for. Remember, the ground is what the truck is measured its velocity with respect to. So the velocity of the truck with respect to ground is positive 60 miles per hour. And positive just means, in this case, we'll call north positive. And the velocity of the ball with respect to the truck is also positive 60 miles per hour. So if we want to know the velocity of the ball with respect to the ground, according to our rule, we need to take the velocity of the ball with respect to something plus the velocity of something with respect to the ground. Well, all I see that I have is a t. So if I put a t on here, then I have to put a t over here. Well, I've got VTG and I also have VBT, so that works greatly. So now all I have to do is say 60 miles per hour plus positive 60 miles per hour. And when I do that, I get 120 miles per hour again in the positive direction. I've been seeing some stuff lately doing this. People are doing this on Instagram and TikTok. Maybe y'all seen it as well. Have you seen anybody where they're riding on like a launcher on the back of a Mack truck, and this back truck has a chair mounted on the trailer, and the chair shoots off like a projectile and throws you off the back of the truck. But they're setting it up to where the truck's going 60, and the person in the chair is going 60 in the opposite direction. And it's just to convince you that, yeah, 60 minus 60 really is zero because the person doesn't feel any pain whatsoever. The truck is going 60. They get accelerated from 0 to 60 by the back of the truck and then just fall off, and they don't fall forward or backwards unless they just lose their balance or something like that. But that's a great indicator. Anybody seen any of those Instagrams lately? I know I saved a couple of them as bookmarks, so I'll see if I can figure out some way to put them on my Canvas station channel so you can see them. But that's a good way of considering how to do this. So, for instance, what if you wanted your velocity to be with respect to the ground to be zero? How would you do that? Well, if the truck was going 60 miles per hour, by this math, it's obvious that the ball would have to go negative 60 miles per hour. So if she turned around and faced the back of the truck and threw it 60 miles per hour, if you were standing by the truck, you'd see something very weird. If you happen to be at the right spot at the right time, you'd basically see her and the truck moving to the right, say, and then at one instance, you would see a ball come to a complete stop and just sit there. However, it looks like it just left her hand, but now she's going off to the right and the ball is just sitting there and it falls straight down because she happened to throw at exactly the same speed, but in the opposite direction as the velocity of the truck. Now, the other thing that goes with both of these rules, both the relativistic one as well as the Galilean/Newtonian one, there's the Galilean/Newtonian one. and there's the relativistic one. But the other thing you need to know is the velocity of I with respect to J is always going to be the velocity of J with respect to I times -1. So everybody see the negative sign there. That's not a misprint. That is an actual thing there. Now, this might not be obvious to you, but hopefully it will after I explain it to you. So let's imagine you're sitting in a car and you're going 40 miles per hour down a highway. Okay. A car goes by you going 60. So you look over to the car at your right. You're both going the same direction. That's the key to understanding this. In order for you to use this fancy addition of velocities equation, you both have to agree what the positive directions are. And when you start doing 3 dimensions, you got to agree that the x is positive in one direction, the y is positive in another direction that's perpendicular to the x, and the z is positive in another direction that's perpendicular to the x and y directions, and both frames have to agree on what's positive and what's negative. Okay, so if you don't have your axes parallel like I drew them, then they're not necessarily going to work. You actually have to have the x-axis parallel to the other x-axis, and both of them agree that, let's say, north is positive and south is negative. So now that you have this idea that two cars, one's going 40 miles per hour due north, and the other one's going 60 miles per hour due north, according to the person in the car, what is, now I'm going to say cars on the highway. So the velocity of car A relative to the ground is positive 40 miles per hour. I know it would be smarter for me to use meters per second because that's what we're supposed to be working in. But right now, I need y'all's complete understanding. And if anything like meters per second would hinder that, then I don't want to use it. We're also going to say that the velocity of vehicle B, as seen by the ground, is positive 60 miles per hour. So since we said they're both positive, that means they're both going the same direction, which we could pretend is north. And what I want to do is calculate what is the velocity of B as seen by A, and then I'm going to calculate the other one, which is the velocity of A according to B, which is just like IJ versus JI. So the velocity of B with respect to A is the velocity of B with respect to G plus the velocity of G with respect to A. Well, the velocity of B with respect to G is obviously positive 60 miles per hour. Now, the velocity of G with respect to A, that's not necessarily something we have. We have AG. But according to this rule that I just taught you, right there, if we make that assumption, then what we can do is we can say minus VAG. So I can replace the GA with an AG as long as I put a -1 in there too. So now I'm going to get plus 60 miles per hour minus 40 miles per hour, which equals positive 20 miles per hour. Okay. So according to you sitting in car A, car B is passing you at 20 miles per hour. But if we want to know the velocity of A as seen by the person in that car, so that person is looking back at your car and saying, oh, that's weird. That car is going to the left, right? Because in their reference frame, forward is the positive direction, but in their reference frame, you are going backwards. So let me show you how that works out. The velocity of A as seen by B is the velocity of A as seen by G plus the velocity of G as seen by B. Again, we have to play a little fast and loose, this is going to be the velocity of A as seen by G because we have that. But I'm going to have to replace the VGB with a negative VBG. So this time I'm going to get VAG, which is 40 miles per hour, positive, minus positive 60 miles per hour. And this gives us, in fact, negative 20 miles per hour. And you can see, of course, I did have to use the Vij equals negative Vji to compute the calculations. But the key thing is it should make some sense to you now that, yeah, according to the person in vehicle B, the vehicle A is actually going backwards, and therefore they have a negative direction. So in order to use this equation, just remember this, in order to use this equation or this equation, you have to remember that this is true too. So this requires us to use this, and this also requires us to use this. I might show you an example with relativity for this velocity a little bit later, but right now I just need to keep pressing on. But that is how we can deal with addition of velocities. I should also tell you that if you talk about an aircraft flying in a jet stream, you might think, okay, well, that's wind, and therefore wind's applying a force to the aircraft, and then I'm going to have to calculate what the force is making it do. It's not that at all. What you have to remember when you're dealing with aircrafts and jet streams and wind and air that the aircraft is flying in, the actual space in which the aircraft is flying is the air. So they automatically are like relative coordinate systems. So just like you riding on the back of a Mack truck that's going 60 miles per hour, when an aircraft gets in a jet stream or some wind flow that's moving at 140 miles per hour, they automatically get a free 140 miles per hour blowing in the direction of the wind, which is great if that happens to be the direction they're going. If it happens to be the opposite direction, then that means it's going to slow them down by 140 miles per hour. If it happens to be slightly perpendicular or completely perpendicular, it's a whole different ballgame. But that's the key thing to remember when solving these relative motion problems. The same thing with a boat in a stream. You don't have to worry about the forces that the water is applying to the boat. You just have to realize the boat is moving on the moving coordinate system that is the stream. So hopefully that'll help. Now, let's bring you to the ideas of velocity, average velocity, instantaneous velocity, all that good stuff. So for starters, I'm going to tell you there's something called speed and there's something called velocity. If you take into account not only how fast something's moving, but also the direction it's going, then it becomes what we call a vector quantity. So if you saw Despicable Me, you probably know the bad guy had a very specific name. Anybody remember the bad guy's name in Despicable Me?
Vector.
Exactly. And he said, it's a mathematical term. It means something that has both magnitude and direction. And evidently he was doing evil with magnitude and direction or something like that. But anyways, that is a accurate representation. Thanks for that too, Darius. That's an accurate representation of one of the definitions of vector. A vector it has other properties, but the main thing you got to think of is the vector differs from a scalar in that the scalar is a number, and that number might be a denominate number. In other words, it might have units, or it might be a pure number. But a vector has a nominate number or a denominate number. Doesn't really matter. It could be a unitless number or not. The main thing is it has a quantitative value that we assume is its magnitude, but it also has something associated with direction. So that's the difference. For that reason, we have this really nice mnemonic that speed and scalar both start with an S. And vector and velocity both start with V's, as in Victor. Okay, so hopefully that'll help you remember it. For right now, since we're dealing with one-dimensional motion, I'll tell you if we just think about the signs that numbers can have, then automatically you're taking into account the direction, because a one-dimensional speed in the positive direction can be indicated by it having a positive sign, whereas a one-dimensional velocity, say, notice I'm switching to velocity now, will actually have an associated direction with it, whereas a speed wouldn't have a direction with it. But a velocity of positive 1 meter per second means it's traveling in the positive direction at 1 meters per second. And if it had a negative 3.5 meters per second, it means it's traveling at 3.5 meters per second in the negative direction. So in one dimensions, that's really all you got to do, and it's not that hard. You'll see when we get to chapter 3 that we're going to deal with vectors, and we'll have to deal with them in more robust ways. But in one dimension, it's pretty straightforward. So first off, what I'm going to give you is the average speed. Oops, I'm going to try writing with a pen as opposed to a laser pointer. So let's say average. Dang it, it still won't let me do it. There it is. So average speed, S, is equal to the distance traveled divided by the time taken. I will remind you that S in the word scalar and S in the word speed tell us that they're both scalars, and vector, the V, and velocity like that. So hopefully that'll keep you straight. So if you want to give an idea of what an average speed is, you might say, okay, in softball, let's say the kids run in 60 feet base runs. Don't worry about whether that's true or not. It's not too terribly problematic either way. But what we're going to do is say this is 60 feet. And then we're going to say this is 60 feet. And then we're going to say this is 60 feet. And then this is 60 feet. Now, back at this place, of course, we have home plate, which all of a sudden I'm drawing a blank as to which way it faces, but I'm going to go with that even though I'm not sure it's right. This is the plate. This is the bag there. This is the bag there. And this is the bag here. So what you can imagine is a little kid hits a ball, and technically they're actually standing like here if they're right-handed, or maybe here if they're left-handed. But this little distance is very, very small. So we're just going to assume that we're going to start timing them when they get to that little dot that I just drew. And let's say a child hits a good hit and then runs for the home run in 2 minutes and 32 seconds. Notice I just put a bar over that. That's how we indicate something's an average. That's one of the ways. Another way we could do is we can put like this. I think I've mentioned this in lab setting before as well. But what we're asking here is a child hits a good hit and then runs for the home run in 2 minutes and 32 seconds. What is his average speed? That's what I'm at, where I put S with a bar over it equals question mark. That's just me avoiding writing another sentence. Okay. So the way we calculate this is we realize that he went 60 feet plus 60 feet plus 60 feet plus 60 feet. That's 240 feet. And now the time taken was 2 minutes. Now 1 minute is 60 seconds, so 2 minutes is 120 seconds. And then 32 would be 152 seconds. So if I want to know what his average speed was, then all I have to do is take 240 and divide it by 152. And I get 1.579 feet per second. Anybody find me making any careless errors, do any addition wrong or anything? That should be right otherwise. So that's average speed. Remember, it's just the total distance traveled divided by the time taken. That doesn't seem too strange. Good, thank you, Ely. That doesn't seem too strange. You'll understand why I'm beating this to death when you get to average velocity. Okay. Now that's the average speed. Now the average velocity is a little bit different. Velocity is a vector quantity. And the average velocity is the displacement vector let's call that x r r r d. It is the displacement vector divided by the time taken. So it's defined, the average velocity is the displacement vector divided by the time taken. So it's in terms of another dimension, another definition. So this displacement vector can be thought of as an arrow pointing from where an object was, I'm going to say at t equals 0.000 seconds, to where the object ended up. So the displacement vector, you can sort of think of it as an arrow that points from where the object was to where the object ended up at the end of the time interval. So for instance, in this idea of the little kid hitting a ball, his initial position is right there. So what we could do is we could say, all right, this is going to be our little coordinate system. Let's let this be X, this be Y. And I'm going to draw a vector called the displacement vector. And this one is d sub I. And that means the initial displacement vector. In other words, when we started timing the person after he hit the ball, he was at that position right there. Okay. Now, if we waited until he ran to second base, then we'd say the displacement vector is this one. And actually, I wanted to do that in a different color. Let me change that. So this is D final, and that's for running to second. So if he was only running to second, that would be your displacement vector. And that's the final position vector. So the displacement vector would actually be this guy right here. Let's draw this in. I'm going to draw this one in green.
Professor, not to lose your train of thought, I got a quick question for you. Are your lessons recorded by
Yeah.
chance?
Yes, they're all recorded and they're put on my YouTube channel, usually the same night, but sometimes it's the next morning.
Absolutely. Okay, Professor, thank you.
No problem. So you see here, I was calling all these displacement vectors because position vectors and displacement vectors are really the same thing. But if you take a final vector minus initial vector, that makes it a displacement vector. So it's sort of okay to call all these displacement vectors. But in the case of talking about a child just running from home plate to second, then the displacement vector would be the vector from home plate to second, that green line. Does that make sense to everyone? So you just imagine a vector in one dimension, it's even easier, okay? Because this kid is sort of being pictured as if he's a bead on a wire that happens to be shaped like a square. So that's okay too. We can just treat that as one dimensional, even though, it's sort of ultimately two-dimensional. But now does everybody understand what I mean by displacement vector? I'll say so the red vector and the blue vector are position vectors. And you don't know yet how to deal with vectors, but I'm telling you that a vector from the first place to the last place is a displacement vector. So now we can calculate the average velocity. What is the average velocity for the child that made, whoa, the home run? So the average velocity in this case, normally we'd put a bar, arrow over it because it is a vector. I'm going to put a bar over it too, so I'm just going to put it up there. And what this becomes is the displacement vector divided by the time taken. Okay. Remember, I told you in displacement vectors, really all you need is a positive sign. Since we're dealing with one dimensional, you only need a positive sign to indicate one direction or a negative sign the other. So what actually the displacement is between the kid, notice the kid steps right here and then runs all the way around and then steps right here again. I'm supposed to take the displacement vector from this dot to that dot. An arrow that points from one point in space to the exact same point in space has a zero length. So the displacement vector is really just 0 feet. And then I'm going to divide that by 152 seconds, and I'm going to get 0 feet per second. Notice the big difference between average velocity and average speed. Y'all see why that's a big difference?
I got a quick question. So the arrows on top of the vectors, those are in the direction, right? Or that's just because it's positive?
So the when you put the arrow over top, that's just how we indicate, hey, this is a special quantity. It's not a number, it's a vector. So you put the
Oh,
little
okay.
arrow over, and then the plain bar with no arrow, that means average.
But the direction in the arrow is always going to go that way, right?
Yeah. Yeah, it doesn't point to the left when it's one way or right the other way. Yeah.
Okay, okay.
Some people put arrows on both sides, so you can do that as well.
Okay, thanks.
No problem. All right, so that's really the weird part about velocity and average velocity versus speed and average speed. One of the common misconceptions, your book will talk about it. Remember, your book has these common misconceptions at the end of each chapter. Then it has problems as well. I highly recommend you reading those, but you get a lot of it just from doing the concept questions. But one of the things that you have to deal with is you have to deal with the difference between speed, average velocity, and that good stuff. And one of the common misconceptions is that the speed is the magnitude of the velocity. It is a lot of times. Okay. Most of the time you can say that and you'd be okay. But to be honest with you, it's not technically true. As you can see, for instance, the magnitude of the average speed here was 1.58 feet per second, whereas the magnitude of the velocity, the average velocity, was 0. Okay. So in that case, you can clearly see that the speed is not the magnitude of the velocity. Now, in a lot of cases, the speed is the magnitude of the velocity, but again, it's not always that way because you've seen at least one case that's not. So be advised about that. Anybody have any questions on that one? Okay, now this is a big thing to figure out all by itself. So let me start off by saying, uh, consider motion given by this is one-dimensional motion, but I'm saying x of t. Okay, so x as a function of t is going to be t cubed minus 6t squared plus 8t. What I'd like to do is, for part A, hmm, and then B, what is the average velocity? Okay, now this one's kind of weird, but I'm going to use something that hopefully you already read your chapter and know this, and hopefully, if that's not the case, you at least went through Calc 1 to the point where you got to what they call the antiderivative, and from there you learn that the velocity is dx over dt. Either way, we're going to cover that next. But the main thing is we found that the velocity was the displacement, the average velocity was the displacement divided by time taken. If you wanted the instantaneous velocity, what you do is you'd say v instantaneous is, remember I told you about the displacement being a difference in position vectors? You could say D final minus D initial. Oops, that's supposed to be a D. Minus D initial divided by T final minus T initial. That's the average velocity that we're familiar with. Remember, I just said you take the final position minus the initial position. Again, you don't necessarily know how to do that right now, but the main thing is you know that you're taking some kind of subtraction. But now what we're going to do is we're going to let the limit as delta t approaches zero, because this quantity t final minus t initial is delta t. If you allow that interval to get very small, what's going to happen is the d final minus d initial is going to get very small. And then you're going to take that distance and divide it by that time, and you're going to get a number. And then you'll try it a little bit smaller time period, and you take the distance and divide it by the time. And if you get the same number to, let's say you want 3 decimal places. If you get the exact same number to 3 decimal places, you're done. If you only get the exact same number to 1 decimal place, then you go smaller again, and then divide the distance by the time. If that's a different number, then you go smaller again. You keep getting smaller and smaller until you get the whole number, the first decimal place, the second decimal place, and the third decimal place consistently being the same thing. Then you've gone far enough in considering what this limiting process is. So that's physically what you do. You literally try a bunch of different small time intervals. You might try the time interval that's 0.1 second, and then you try 0.01 second, and then you try 0.001 second, and then 0.0001 second, so on and so forth. But once you got two answers in a row going from one size to a smaller size, if you got the same answer in both of those choices to the number of decimal places you wanted, then you can stop. You don't have to go any farther. Okay. So that is the idea of it. So for this, we're going to say solution. Now that little part where I wrote about the vector, about the velocity, the instantaneous velocity there, that was a sort of quick and dirty derivation, and it basically just says that V instantaneous is equal to D. Well, we called it capital D before. I guess I can still call it that. D displacement over dt. But you could also call that dx over dt, or you could call that, what I prefer is dr over dt. And that's why I had told you earlier that the displacement could be x or r or d, because those are normally vectors that we use to recognize or to label position. So for part A here, now that we have that information, that'll allow us to figure out from this x of t up here what the actual instantaneous velocity is. The speed, I just need to know the distance traveled. So if I were to look at this equation, I'm going to go ahead and say part A here. X is equal to t cubed minus 6t squared plus 8t. I know I can factor out a common factor of t from there. That's going to give me t squared minus 6t plus 8. But I also know that this could be t, it looks like it's going to be, they both have to be a minus. And then I need a product that gives me 8, and that adds to give me 6. So that's 2 and 4. So that's what that function is. And now, because of that, I know I can graph the function. You might not understand why I have to graph it right now. You will see in a second, though. Okay, what we just discovered was that this function has zeros at x equals 0, x equals 2, and x equals 4. So I'm going to say right here is 0. Right here is 2, and right here is 4. Now I can see that it's t cubed. So x approaches infinity implies, or excuse me, t approaches infinity. X approaches positive infinity. And if t approaches negative infinity, then x approaches negative infinity, even though that one's not a meaningful thing. That just happens to be what our equations are. So that tells us this graph is going to go up from this point and down from this point. Now, the fact that we have zeros means that that's just going to be x equals 0 at t equals 0, t equals 2, and t equals 4. Okay. Now, you can also probably tell that between x equals 0 or t equals 0 and 2, this graph is going to have a maxima to make any sense. So we're going to expect it to do like this, and then we're going to expect it to do like this. That's going to be what the graph is. Now we should check it just to make sure. So x of 1 would probably be about the easiest thing to compute. So that'd be 1 cubed minus 6 times 1 squared plus 8 times 1. That would be 1 minus 6 would be negative 5 plus 8. 8 minus 5 is 3. So this one would be 3. And then we could also try right here. Probably the easiest would be x evaluated at 3 seconds. And this one should come out negative. So I'll be saying 3 cubed minus 6 times 3 squared plus 8 times 3. 3 cubed, well, square would be 9, and then times 3 again would be 27. So we're looking at 27, and then 6 times 9 is 54. And then 8 times 3 is 24. So, oops, I said 20 for some reason, 24. So I'm going to say 24 plus 27 is 51 minus 54 would be negative 3. So this spot right here is negative 3. Okay, that's critical because we really needed to know that. Now, remember, this is all one-dimensional motion. So what this graph is saying that the person took off at t equals 0 second and walked a distance of 3 meters to this spot right here. Then they walked 3 meters backwards to this spot right here. And it doesn't mean they necessarily walked backwards. It just meant they walked the opposite way they came before. And they continued to walk another 3 meters to here. And then they continued to walk another 3 meters back to here. So that their total distance traveled was 3, 6, 9, 12. So S average is 3 plus 6 plus 3, 3 plus 6 plus 3, and that should be 12 meters. All that divided by 4.00 seconds, that'd be 12 meters divided by 4.00 seconds, which would be 3.00 meters per second is the average speed. Notice how I did that? That's a little more complicated, but this is what you have to be able to do if they ask you for an average speed and they give you x as a function of time. You have to understand what the curve looks like. Now let's try part B. Part B, v of t is equal to dx over dt. We happen to have the dx. if I take the derivative of x with respect to time, I'm going to get 3t squared minus 6t plus 8. Oops, minus 12t, I should have said. Sorry about that. So 3t squared is right, minus 12t, oops, and then plus 8. Okay, so that's the velocity as a function of time. In order for us to actually figure out the average velocity, I've got to actually take the displacement over the whole time period. In this case, that's actually how you get the velocity, but that is not how you'd get the average velocity. Remember, the average velocity remember that is supposed to be the displacement. That means a vector that points from where you were to where you are now. And obviously that means I have to point from x equals 0 to x equals 0. So in this case, notice this is just like the kid running bases. At t equals 0, he was at 0 meters. At t equals 4 seconds, he was at 0 meters as well. So the distance is 0 meters divided by 4.00 seconds, which is 0 meters per second. Now, if I had done something like at 3 seconds or 3.5 seconds, then I wouldn't have got 0 for the average velocity, and I would have gotten something different for the average speed too. So that's another fair game. But either way, I'll call point C. I'll call that C. Oops. So erasing this, since we didn't need it, I'm just going to call this part C. And then I'm going to call this part B. Okay, so the average velocity, remember, is the displacement divided by time. And because the t of 4 seconds has a position x equals 0, and the t of 0 seconds has a position x equals 0, then the displacement vector is a vector that points from 0 to 0, and therefore its length is 0. Therefore, you divide the magnitude by 4 seconds, and you still get 0. Any questions on that? And now you've also seen a little example of how to compute the instantaneous velocity. So anybody have any questions on that? Well, let's go ahead. I'm going to give you guys, let's give you an 8-minute break. So let's come back at 7:01. That'll give you a full 8 minutes. So everybody come back at 7:01. When you get back, you can chat me your first and last name. You can do it now too. I'm going to be here the whole time in case you need anything, but let me know.
I had a quick question to ask you.
Yes, Isham.
So the next 3 weeks for me, I will be traveling because I have to get my visa stamped and a whole lot of stuff with that.
Gotcha.
So I know that we have that exam on the 2nd or the 5th, right? And so I don't know if I'll be able to get that, proctored and whatnot. But as I'll be traveling, I'm planning on getting back on the 16th.
Okay.
So
Remind me like maybe a couple days before, or maybe as soon as that test becomes available, just remind me, and I'll give you an extended period. Like you'll get a couple extra days if you need, or you can take it beforehand, whichever you prefer to do.
Okay, sounds good. Is there do you have a way that like I could take it like with my camera on or something like that, or like do you just want me to just take it at another day instead?
I would prefer you just take it another day. There's ways we can do it with cameras, but I normally require people to go out and if they don't own one, they have to go out and buy a mirror and stuff like that. So I don't want you to have to do that unless you absolutely have to, and that's sort of a last ditch effort to get one.
Okay, yeah, sounds good. Yeah, because the thing is, right, I don't know how much flexibility I'll be having with it,
Mm,
uh, according to like the process and everything with the visa stuff, because I'll be going out of the country to do it and stuff.
right.
So I don't know when I'll be coming back exactly. My hope is that I'll be coming back by the 16th, but I have no guarantee, exactly when I'll be coming back.
Yeah.
So
Hopefully everything goes smoothly and you can get back in no problems. And if
yeah.
you, if you can't, then I'll hold it for you and we'll give you incomplete until you can get back or whatever. But yeah, we'll work with you. Don't worry, Isham.
All right, sounds good. Thank you so much.
Is it Isham or how do
It's Isham.
Isham? Okay, that's cool. I'll do my best. Like I said, we'll work with it. We'll get through there.
All right.
All right, got about 6 more minutes for everybody.
I have a quick question with C.
Yes.
The equation is the answer, just straight up.
Yes, it's the 3t squared minus.
It's the derivative of the okay.
Yeah.
Okay.
If I ask you what's the instantaneous velocity at 2 seconds, then you'd have to plug in the t equal 2. But that's about the only difference you could.
The instantaneous velocity at a specified time.
Exactly.
Okay.
So that gives it to you for all times. What you'd assume is between t equals 0 and any future time up to infinity. Although
Mhm.
accurate for up to infinity, but the main thing is that's what that's supposed to be. And then if you plug in a specific time, that'll give you the instantaneous velocity at that time.
Okay.
I have a quick question. Is this Zoom class mandatory for physics 241 um 0 or 001B?
1B. No, it's not.
It's just it's there for you, so you can have it, but you don't have to attend. Basically, what I'm doing is I make the videos up. They're part of the class, so it's something you should watch for best results. But it's just like attendance, you don't necessarily have to come to a college class in a lot of cases, so you don't necessarily even have to watch the videos. Uh, but it would probably not be very beneficial if you didn't. So at least watch them. But yeah, you're not required to be here.
Okay, are we graded on attendance though?
Yeah, not at all.
No, okay. I was just more curious. Thank you.
Uh, it immediately reminded me of another question for 001B.
Okay.
It's about lab one, about the fact that the addendum was not there until I think literally just now.
Right. So, what's your question?
We have an extension on lab one, 001B.
Yeah,
Okay.
I told him you could probably even turn in as late as next Tuesday.
Okay, because that was not there last week. Like it was not possible to do lab one because of it.
Are you one of the people that texted me? I saw like 3 people texted me, and I didn't get to it till this
I
morning.
did not get it. I did not get it within Friday. I did not get the email within Friday, and I did so I didn't bother.
Oh, gotcha. Well, yeah,
Yeah.
no problem. Just turn it in by at least before Thursday, Tuesday of next week, and you should be fine.
Okay, gotcha. Yeah.
I would try to do it quicker rather than later, but the Tuesday
Mhm.
since we have a lab this Tuesday. We are going to have a lab Thursday, but we're not going to have a lab today. And so, uh, because of that, it'll be sort of perfect for you to get it done before then. Anybody else? Still got about 2 more minutes. I do like that you guys are coming, my O01B class. Last semester I had a O01B type class, and two students didn't know I was even holding the meeting, so I guess they thought I was like running a correspondence course. So, I don't want the course to be that. I really want you guys to interact with me as much as you can, or at least get enough of information so that you can solve physics problems. And then if you need me, make sure you contact me. All right, so it's about time to go. So uh, we've talked about basically speed as distance divided by time. Remember, these are the formulas. Don't go crazy thinking, well, average means blah blah blah, and therefore I can do. So I've seen students will take 3 or 4 speeds and they'll add them up and divide by 3 or 4 and say that's the average speed. That is not the definition of average speed. Average speed is the total distance traveled divided by the total time taken. Average velocity, on the other hand, is the magnitude of the difference in the position at t equals 0 and the position at t equal whatever the end is. Once you take that distance, that difference in positions, that comes out to be some number of meters or feet or inches or something, and you divide it by the time taken, that is the average velocity. So if, for instance, the initial and final position are the same place, then that initial distance or that distance is 0. So when you divide 0 by anything, you get, of course, 0 unless it's 0, and then that's undefined. So we did do that. Now I want to move a little bit further and go on to something called acceleration. So far, oops, I don't know why I made that one word. We have S bar is equal to distance traveled divided by time taken. We have V bar is equal to displacement divided by time taken. And this displacement is the final position minus the initial position. So we've got that, and we also found that V instantaneous is equal to, let's take the limit as delta t approaches 0 of x minus x0 over t 0 plus delta t minus t0. That's another way that you can write that quotient, that difference quotient that you remember from pre-calculus. But the main thing is it's dx dt, and we're still talking about one-dimensional motion. So if you think about Galileo's definitions, his average speed, or his speed idea, was basically an object with a constant speed or a constant velocity would basically cover the same distance in a given unit of time. So if you took that time to be 1/10 of a second, it might have moved 12 centimeters. But if it's going at a constant speed or a constant velocity, then it's always going to move 12 centimeters in 0.1 seconds. If, however, we consider the case where it changes, in other words, it covers a different amount of distance in a given unit of time, then we would call that accelerated motion. And in fact, accelerated motion is motion where the speed changes or the direction changes or both changes. Okay, so you can speed up or slow down, or you can turn left or turn right. You can hit the brakes. All those different things are ways to accelerate. And what we'd like to do is quantitatively discuss acceleration. So what Galileo decided was accelerate. I think it was Galileo. So what acceleration is the change in the velocity divided by the time taken. So the average acceleration is equal to v final minus v initial, or actually, since I've been using no subscript with the O, I'm going to go ahead and try to stick with that. So I did x minus x0, so I'm going to do v minus v0. I could have made it v final minus v initial, or v final minus v initial, or v0, either one. The main thing is they vary from place to place and time to time, so be aware that sometimes I'll change it up. And again, I'm going to say this final time is t0 plus delta t, and then I'm subtracting from it the initial t0. So that again is our average acceleration. Notice I take it and take the final velocity minus the initial velocity, and I divide it by the total time taken. So that's what all this fancy junk on the bottom is. Okay. So that's our average acceleration. So does anybody have any data or any facts they can tell me about a car? Like if you were wanting to go in and buy a really fast car, a car that could really get up and go, do y'all know of any data that would suggest it has a good acceleration or a bad acceleration? Horsepower is directly related to horsepower. Another one someone said is 0 to 60. That's the one I was looking for, not because the other one's wrong, just because it's more directly associated with it. So a typical thing that people will claim if they want to say their car is fast, and this used to be a really big deal, like the Mustang GT, uh, or the Camaros or the IROCs and all those different mid-level American sports cars would brag that they were 0 to 60 in 4 seconds, or 0 to 60 in 3.9 seconds, or something like that. But let's take that. Let's take 0 to 60 in 4.0 seconds. Oops, I know I'm going to, oh yeah. Now, this used to be a big deal, and I say it's not a big deal anymore because if you've heard anything about it, for instance, the uh, Tesla Plaid can go 0 to 60 in 1.9 seconds. So this is a really big deal. And the Cybertruck is approaching 2 seconds as well. So that's kind of a big deal. But 0 to 60 in 4 seconds, that should immediately tell you, hey, I've got an average acceleration that I can calculate from that. The final velocity is 60 miles per hour minus the initial velocity is 0 miles per hour. And then the time taken is 4.0 seconds, 0 seconds plus 4.0 seconds minus 0 seconds. So I tried to write it in the same form we had before. You can see really what's happening is the 0 seconds are going to cancel out, and I just get 60 miles per hour divided by 4.0 seconds. And that gives me 15 miles per hour per second. That is a perfectly usable acceleration. It's not the normal one that we would use in this class, but you can use it and you can understand it. In fact, you might look at t equals 0 seconds. The car is going 0 miles per hour. T equal 1 second, the car is going 15 miles per hour. T equal 2 seconds, the car is going 30 mph. T equals 3 seconds, the car is going 45 miles per hour. And T equal 4 seconds, the car is going 60 mile per hour. Now that's not necessarily accurate. This is all assuming the acceleration is constant, and I guarantee you the acceleration will not be constant. In fact, it'll be a very high acceleration when you first hit the pedal, maybe a low acceleration for like the first half a second, and then like from there on out a really high acceleration, and then it'll start to chill out once you start getting around 30, 45 miles per hour. It won't have nearly as much pickup. But the main thing is that this tracks. So this is an idea of acceleration. And because of that, I hope that it will help you remember the formula for average acceleration. So the formula for average acceleration is V final minus V. Oh, I said I was going to do it without this F subscript. So it's going to be V minus V0 over T minus T0. So that is our average acceleration. And you might have figured out that if we allow the time interval to get smaller and smaller and smaller, what will happen is if you had a graph like this is time, this is velocity, and you had some giant curve like this, and this, for instance, was t0, and this was t, and this was delta t. If you allowed the delta t to get smaller and smaller, what would happen is this dot would move closer and closer and closer until basically you would get the slope of this little graph is equal to delta v over delta t. And since you're taking the limit as delta t approaches 0, I think you can probably see that A instantaneous is equal to the limit as delta t approaches 0 of v minus v0 over delta t. I just wrote it with a delta t this time so in hopes that it'd be a little less complicated looking for you guys, but that's basically it. It's still the same formula, v minus v0 over t minus t0, or t plus delta t minus t0 plus delta t minus t0. That would be acceptable as well. But now we have that, and because of this, we can do a lot of really good things. We can go ahead and start, for instance, deriving formulas for kinematics. So what I'm going to do right now is I am going to show you a couple of examples. And let's see. Let's see. A car going in the positive direction goes from 30 meters per second to 40 meters per second in 5.00 seconds. What is the average acceleration? So the average acceleration in this case A is equal to V minus V0 over, let's say T0 plus delta T minus T0. That will work out fine. So the final velocity is 40 meters per second minus the initial velocity is 30 meters per second. And then the delta t is the 5.00 seconds, and this would be 0 plus this minus 0. So what you get is 10 meters per second divided by 5. That would be 2.00 meters per second every second. Now, you can actually record this as meters per second squared, and you would be mathematically correct. But for you to have some understanding of what acceleration is, I highly recommend you call this 2.00 meters per second per second. Notice the object was speeding up. I should write this right. It was speeding up. And A was positive. A lot of people are going to think positive acceleration means speeding up, negative acceleration means slowing down. That's not the case. That's what I'm trying to teach you here. So I'm pointing this out. Let's see example B. A car going in the negative direction goes from negative 30 meters per second to negative 40 meters per second in 5.00 seconds. What is A bar? So A bar in this case is V minus V0 over T0 plus delta T minus T0. Again, using all that crazy stuff, you don't have to use that. Of course, I'm just trying to keep it consistent with some of the stuff I wrote and some of the stuff you've seen. So in this case, the final velocity is negative 40 meters per second minus negative 30 meters per second over 5.00 seconds, which would be plus 0 on both sides of that 5, but we don't need that. So negative 40 minus positive, or minus negative 30, which is plus positive. So it'd be 30 minus 40 would be negative 10. So that's negative 5.00 meters per second every second. So in this case, you see it was speeding up, but it was going in the negative direction. And this time you got A was a negative. So hopefully you can now see that acceleration being positive does not necessarily mean speeding up. It could mean slowing down. It could mean speeding up. It all depends on what coordinate system you're using. And of course, like I said, that's all associated with, there being a positive direction for each dimension. We're dealing with only one-dimensional motion here, so we don't have to think about the other directions, but still we have to think about one direction being positive. Maybe it's north, and then south would be negative. Okay. Now that we have that as examples, hopefully you have a little bit better understanding about that not being the positive not meaning speeding up and the negative not necessarily meaning slowing down, but also you want to know what the units are. So remember, this is meters per second, which is the same thing as meters per second squared. That's completely fine to say meters per second squared, but I highly recommend you, at least in terminology, when you're saying the words, say meters per second every second. Because what that literally means is if this car actually had a true constant acceleration of, and I don't know why I said 5, that was supposed to be 2. I'm sure one of y'all would have caught me on this in a second. 10 divided by 5 is 2. So this being 2.00 meters per second every second literally means that if you watched it at 0 seconds, it would do nothing. but from 0 to the first second, its velocity would decrease by 2 meters per second in that 1 second. And then after 2 seconds, it would drop by another 2. And then after after 3 seconds, it dropped by another 2. So that's literally what we're meaning is the velocity is going to change additively by what the acceleration is. So when the acceleration was +2, that means 2 meters per second is going to be added to the velocity each second. That's why we call it 2.00 meters per second every second. Hope that helps. Now that we have some of these, I will also point out, by the way, that given that, ooh, turning back here, I forgot to put the right-hand side of this. Remember, A instantaneous equals the limit. Well, that's going to be dv over dt, which we already learned v was dx over dt. So this turns out to also be d2x over dt squared. So that is really what the instantaneous acceleration is. It's the derivative of velocity with respect to time, or you can think of it as a second derivative of position with respect to time. Now that we have that, I'm going to show you rather quickly how we can derive the kinematic equations. And this method that I'm using here, I'm going to be doing it with just symbols, but you can translate this to an actual real physical problem with numbers, and you're going to have to be able to do it the same way. So let's say consider an object undergoing a constant acceleration of a. So a is supposed to be just a scalar. If at t equals 0, its velocity was v0 and its position was x0, then what are its position and velocity as functions of time? So that's our big problem. So the way I work it out is as follows. And notice you're going to do the same thing with yours. This one, yours could be something where instead of them having a, they might say the acceleration is 3 meters per second. Or they might even be radical and say it's 3t plus 7t squared or something like that. And they might even follow up and say, well, what must the units of that number in front of the t be? What should the units of that number in front of t squared be? All of those would be fair problems, so keep those in mind. We know A is dv dt, and we know v is dx dt, and we know A is equal to a constant. V0 is a constant, and x0 is a constant. So I'm going to start off with A is equal to dv dt, and I'm going to multiply both sides by dt. And now I'm going to integrate both sides like this. And I'm going to integrate from t equals 0 to t. Mathematicians don't like this. They prefer us to call that like t prime. The dt would be dt prime. And then we'd integrate from 0 to t. I'm going to ignore all that. And this one is from v equals v0 to v equals v of t. Okay. So we can see that the a dt just gives us a times t minus t0. Notice because I gave limits of integration, I don't have an integration constant. Now for the right-hand side, I have to use the fundamental theorem of calculus, which basically is the thing that tells us the integral is the antiderivative. We've got an integral of a derivative. So what we get is just v of t minus v0. So now we can say v of t is equal to v0. Oh, t0 was actually equal to 0. Sorry about that. I'll just put minus 0. So this is just v0 plus at, like that. That is the velocity as a function of time, and that is one of the solutions that we were asked for. Now, the other thing we remember is v of t is equal to dx dt. So now I can say v0 plus at times dt. In other words, I'm multiplying both sides of this equation. I'm multiplying both sides of it by dt. This was v0 plus at, and now this is me multiplying it by dt. Now I'm going to multiply this by dt. Oops. I'm going to use a pen. So this is dx over dt times dt. And now I'm going to integrate both sides. And I'm going to integrate from t equals 0 to t. And I'm going to integrate from x equals x0 to x equals x of t. So again, I'm going to use just our normal integration on the left-hand side. So the integral of v0 is v0t. And the integral of at with respect to t is 1/2 at squared. And once I evaluate them at t and 0, I get exactly the same answer, so I'll leave that. Now the other side, using the fundamental theorem of calculus, that's going to give us x as a function of time minus x sub 0. So I get x of t is equal to 1/2 at squared plus v0t plus x0. So this is one of our kinematic equations as well. As long as we're dealing with constant acceleration, you can use this equation, which will normally be written not as x of t, it'll just be written x. And the v will not be written v of t, it'll just be written v. And that's our kinematic equations. Now, I can get another equation if I solve for this. I'm going to call this equation here equation 1. I'll call this equation 2. We can get another kinematic equation by solving 1 for t and plugging that that into 2. So I'll proceed as follows. 1 gives me t is equal to v minus v0 over a. Notice that is what used to be called v of t. Now this and 2 gives us x is equal to 1/2 a v minus v0 over a squared plus v0 v minus v0 over a plus x0. Now I could say x is equal to 1/2 a, and now I'm going to say v squared minus 2v v0 plus v0 squared, all that divided by a squared. And then I can carry through with this one and get v0 minus v0 squared over a plus x0. Now what I can do is get rid of that 2 there by canceling out the a above, and now I can multiply by 2 over 2, and I have a common denominator, and by doing that I can get v squared minus 2v v0 plus v0 squared plus 2v v0 minus 2v0 squared. Hold on a second, I got kind of small in there. Let me use an advantage that y'all don't have. This will be, looking back at it, this is minus 2v0 squared. Like that, and then all of that will be over 2a, and then we still have the plus x0 all by itself, which I'll leave right there. So now what we can do is we can see x minus x0. In other words, if I subtract x0 from both sides, then I get x minus x0 on the left-hand side, and on the right-hand side, I get v squared, because that term survives, minus 2v0 plus 2v0. Those two things are canceling each other out. And then I got v0 squared minus 2v0 squared. That's just negative v0 squared over 2a. So finally, I can write this as v squared is equal to v0 squared plus 2a times x minus x0. And this is our third kinematic equation. Okay. We also have the average speed equation, the average velocity equation. I think you see the average acceleration equation is the same as equation 1, but we still have all those. So those are our kinematic equations, and that's the equations we're going to use repeatedly to solve various physics problems. Remember, as long as the acceleration is a constant, even if that constant is 0, all these equations are valid. I will tell you that a lot of instructors will not let their students use equation 3 because equations 1 and 2 are consistent with vector equations, which we'll introduce next chapter. But 3 is inherently about a non-vector quantity because the square of a vector is not a vector. So some instructors just won't let you use that. Remember what the terms are. The V's, things without subscripts, are either the average value or basically the constant value or the final value. So for instance, in equation 3, v squared equals v0 squared. The v squared is the final velocity once it's gone from x0 all the way to x. V is the velocity it'll have when it reaches the x position called x. and v0 was the velocity it had at the x position called x0, and a was the constant acceleration it had. So x0 was the initial position the object had, a is its acceleration, v was the velocity it had at t equals 0 in equation 2. Hopefully that helps as well. So let's look at another type of example doing just this particular problem. This is the sort of the harder stuff. A lot of the stuff we're just plugging in the kinematic equations to solve physical problems. Those are a little bit more easy, and hence I'll leave you to check out those examples. I'm trying to give you the ones that give students the hardest time. So here's another one. Let's say if an object has an acceleration of a of t is equal to 2 squared t squared minus 3, then, let's see. And initial velocity, oops, of 2.00 meters per second, and an initial position, oops, of x equals 1.00 meters, then what are v of t and x of t? So these are basically trajectories or orbitals is the x of t. The velocity is just a velocity as a function of time. We can, in principle, do this. I would also follow up with a question on this. I would say, what are the units of what are the units of 2, well, and 3 in a of t equals 2t squared minus 3. So that's also a nice follow-up question. So I'm going to show you how we're going to do this. For starters, I'll start with the bonus question. So the units of A is equal to the units of 2t squared minus the units of 3. The units have to be meters per second, and that means the 2t squared has to be units of 2 times seconds squared minus the unit of 3, like that. So we're almost getting to it. I can call this meters. I'm going to call this meters to the 1 power and second to the negative 2 power. And now this is going to be the units of 2 times second squared minus the units of 3. So we can already see, if we just look at the fact that each of the terms on the right has to equal the thing on the left, then we can say m to the 1, s to the negative 2 is equal to the unit of 2 times s to the positive 2, which means the unit of 2 is going to be equal to meters to the 1 s to the negative 4. Similarly, we can say meters to the 1 s to the negative 2 is just equal to 3, and that one's a no-brainer. 3 must have units of meters to the 1 seconds to the negative 2. So those are what those units are. Hopefully that helps you a little bit, but that's a typical question I will ask you, or other instructors will ask you for such physics problems. Now let's get to the more pressing problem. So what we have is a of t is equal to 2t squared minus 3. But we also know that a of t is equal to dv dt. So if we use that, we can say 2t squared minus 3 is equal to dv over dt. I'm going to multiply both sides by dt and then integrate, like I did there. And when I do that, that's going to give me, we're integrating, so we're actually going to go up by 1, and that's going to be 2t squared is going to become 1t to the third. I'm also, by the way, integrating from t equals 0 to t, and from v equals v0 to v. The t and the 0 just means this 2t squared, when I integrate it, becomes 2/3 t to the third power. That I almost made a careless mistake there. Hopefully some of y'all caught me on that. The integration of 2t cubed would be, or 2t squared would be 2 t cubed over 3. And then, of course, the integral of 3 would just be negative 3t. And again, that's evaluated at t and then evaluated at 0, and the 0 terms are 0. So that gives me that. The right-hand side is just the fundamental theorem of calculus, and that's going to give me v of t minus v0, which we found was 2.00 meters per second. So I can now say that v of t is equal to 2/3 t cubed minus 3t plus 2.00 meters per second. And that's not only the velocity as a function of time, but remember, with the bonus part that I did, that gives you what the units of the number 2 is, as well as the unit of the number 3, the coefficient of t. So we've got that. Now we can go ahead and find the position as a function of time by recognizing that v of t is dx dt. And because of that, we can set all this equal to v of t. So we're going to say 2/3 t cubed minus 3t plus 2.00, dropping the units for right now, is equal to dx dt, like that. But now I'm going to multiply both sides by dt and integrate. And this one's going to be from x equals x0 to x of t, and this is going to be from t 0 equals 0 to t. I think you can see that the integral of 2/3 t cubed would be 2/12 or 1/6 t to the fourth. Make sure you're watching my work here. There's a good chance I'm going to make a ton of errors. I'm surprised I haven't already. So that's 1/6 t to the fourth minus 3 halves t squared plus 2t. Just remember that's the 2 that we had that was just by itself. So that one has the units of meters per second. So that's the left-hand side, and that's taking into account the limits of integration, which were t and 0. The right-hand side is just the fundamental theorem of calculus, and that's going to give me x of t minus x0, which x0 we said was 1.00 meters. So now I can say that x of t is going to be 1/6 t to the fourth minus 3 halves t squared plus 2.00 meters per second times t plus 1.00 meters. And that is the position as a function of time. So that's about the nastiest of the types of problems that we would work. Anybody have any questions on this? Now, it might seem scary because there's so many steps, but it's really not that big a deal. It's just the same thing over and over again. If you look at the last section in chapter 2, which basically we just finished, but if you look at the last section of chapter 2, he does it his way, very much similar to the way I did mine. This one I just chose to put my limits of integration in and stuff like that. But he actually explains it, and it's more or less not the same as this problem, but it's more or less the same of this problem where we said the initial acceleration was just playing a constant a, and the initial position was a constant x0, and the initial velocity was a constant v0. Your book actually goes through this in detail and more or less repeats this. So all you have to do is read that, then come back, look at the video of this. If you still don't get it, give it one more try. And then by then, it'll probably be stuck in your head so well that you'll actually be mulling and stewing about it from time to time on your own, even when you're not doing work. So all of that turns out to work in your favor, where eventually you'll get it or you'll have it memorized where you can at least regurgitate it. Hopefully, by the end of the semester, you would have it completely internalized and understood. But if you don't, that's not completely abnormal. It just might make it a little harder until you do get that. But just keep on plugging away and you'll get it. Anybody have any questions on anything? I had already told everyone to chat me your first and last name just before the last break or before the break. And remember, include asynchronous or O015 if you're one of those students. Put that with your name too. If you've already done it, of course, you don't have to. But you guys are actually free to go. I think that's about it. If you have any questions, I'll be here. I'm just waiting for the last person to leave, and then I'll split.
Sorry, I just have one more question. When you mentioned that the tests are open the whole week to
Mhm.
take them, is that the same with the final?
The final, yeah, I usually leave that open at least 6 days, but sometimes I'll leave it 8 days. It's just so that various students can take it at various times. But again, each student's version is slightly different. So I sometimes I'll just change individual numbers on the problems where answer A for number 4 becomes answer B or something weird like that for but they're essentially the same in context, but not completely identical.
Okay, thank you so much.
All right, you're welcome, Jamie. Anybody else? You're welcome, Eli.
We have a test this week.
I thought I moved that back, but it might be due Monday. Let me double check my syllabus.
This upcoming Monday.
Yeah, meaning it's due this coming Monday on the what would that be, the 30th?
The 2nd of May, the 2nd of June.
Yeah, that shouldn't be a
Oh
problem.
my
Like I
god.
said, it's an online one. Remember, you get
We're
3
both sections too.
Yeah, it's 2 chapters. It's chapter 1 and chapter 2. But remember, dude, it's like you get 3 chances, only your highest grade count, open book, open notes. It's really just taking a practice test and getting some credit for it. Whereas the practice test normally only gives you extra credit and only if you do it, just right. This one just gives you credit right now, makes you feel better about your ability and that sort of thing. So give it a try. If it turns out to be too onerous, I'll consider next semester or maybe even later in the semester dropping the online test. It's been my experience that students, even though it's in some sense more work, they are a lot happier with their grades. That's why I went to this.
Okay.
Okay.
Okay. Gotcha.
Don't have a cow, man. It's gonna be all right. Anybody?
Hey, Professor.
Yeah,
So
buddy.
when will the first in-person test be?
I would refer you to the syllabus, but I want to say it's about 3 weeks from now. I want to say it was like June 17th or something, maybe. But if
Yeah, I'm looking at it currently, and I just don't see it up here for me.
okay, let me pull it up then and see, because I might have done something goofy. I don't know. That does happen. There we are. You're in N02B or are you in O01B?
I believe to be
Okay, so you're the one that's supposed to be in this class right now. All right, let's check that out. Syllabus.
correct.
And let's see if it's face to face. Oh, yep, it's been erased. Now I gotta go find it. That did not change from the last test. I mean, from the last syllabus. So let me pull up the old syllabus. I'm gonna go to modules. I just left the link syllabus on the left hand side. I'm going to modules. I'm going to helpful documents and links in your modules. And down below syllabus, you'll see 241 N02B L01B summer 25. That's the old one. So I'm opening it up because I don't recall changing that date and I don't think I will. Uh, nope. Okay. Not being as receptive as I'd like. Hold on, take me a second here to get. I have to go to my actual file on my computer to do it because otherwise it's just a pain in the butt. It'd be too much of a pain to deal with. So here I am. Oh, and I love the system the Apple's got. Like everything's upside down. Oh. Okay, summer. No, we are there, and you're the N02. So that brings here. That brings almost there. All right, that's the one I was looking for. Okay, so this says the first face-to-face test is that's due 6/9. Oh, so it's a little earlier than expected. So it's literally next week. Yeah, okay.
Okay, thank you.
All right. Sorry about that, Michael. Anybody
No
else?
problem.
Hey, Professor, quick question. So, if I wanted to take the test that's due June 3rd, the first test that's non-proctored, I can
Mhm.
take that at any time. Like I can take that at 2 in the morning this Saturday if I was available.
If it's non-proctored, yeah. But if
Okay,
it's
great.
proctored, you have to obviously meet the proctoring standards. But yeah.
Yeah, I'm not in Virginia at the moment just because I'm military. So I'm gonna reach out to my ESO. And you said he should be texting you no earlier than 1 week, but it has to be at least 1 week before if he's in a proctor, so he can apply to be a or like fill out the form with you.
Yeah, if he does it a day or two earlier in the week or a day or two after, less than a week away, then that's fine. I'm not trying to be strict. I just want to make sure somebody didn't email me one day and expect me to do it the next. So I usually do.
Okay, that's understandable. I'll have him reach out to you. Or I'm gonna reach out to him so that he can contact you.
Okay, what are you in North Carolina instead of Virginia?
No, I'm in Portugal right now.
Oh, good. That's a little bit further away than.
Yeah. That's why I say like if I'm available, like obviously it might not be 2 in the morning, but just the time zone's different. That's where I'm getting at.
Gotcha. Yeah, yeah. That'd be totally different. Yeah, there's no problem with that. Don't worry about it at all. Let me
All
know
right,
if
Professor.
I can do to help you.
All right, thank you so much.
Thank you for
All right.
serving. Adrian, you have anything?
Yeah, I think it was just one of the problems. It was one specific rapid estimation problem from the first one because I did so horribly on the first homework.
Oh, would you make a bad grade on the homework, the whole assignment, or just that one problem?
I did not do one of the questions and then the basically the four parts of uh estimating a prop estimating something order
Uh-huh.
of magnitude. That order of magnitude problems was probably my worst one.
Yeah,
I was
that
probably going to ask
usually
about the last one,
is.
specifically the Archimedes bathtub question,
Okay. I think I
because I
saw.
did not understand a single aspect of it. Because
Uh,
the I immediately thought I had to look for the volume of the bathtub.
uh,
Instead, it gave the weight.
I'm gonna pull it up real quick just to check, so I can see what you're talking about. We're talking about.
It's the one about the Archimedes, the bathtub from Archimedes.
Is it conceptual or homework?
Homework. This is homework. Conceptual, I did okay. The homework was ass.
Made to order Neptunium converting consistency of units.
I think it was the last one of the problem.
Okay,
The last one.
let's see. This does not look like it. Nope. For small angles, no, that's not it. Let's try. Yeah, don't have that descriptive text on my side. Uh,
It was essentially how many molecules of water existed in Archimedes' bathtub. I think it was something like that.
gotcha. Yeah, that one's a
I
little
think
even more complicated because I think they're using a probability on that one. Answer statistics on the page, a certain audio, compact disc. No, that's not it. 1.51 is not it. Jesus, I can't find it at all. Density of an object is defined as mass divided by volume.
so. Did I just luck out horribly with that problem?
I don't know. I can't even find it yet. I'm still looking at the density problems. I think that was that one. Yeah, that's the small angle
I
approximation.
think it was how many molecules of water. It's not like a density. Yeah, I remember it being how many molecules of water, I believe.
Yeah,
And then it was a story about Archimedes running through the city naked.
I swear I can't find that problem anywhere. I was looking for the actual wording, but legend has it. Oh yeah, here it is. Legend
Yeah.
has it, many centuries ago, Archimedes jumped out of his bathtub and ran across town naked, screaming "Eureka!" after he solved an especially difficult problem. Though you may not have thought of things this way before, when you drink a glass of water, the water that you are drinking contains some water molecules that were in Archimedes' bathwater that day. Because water doesn't get created or destroyed on a large scale, it follows that the water from Archimedes' bathwater has been through this cycle enough times that they are probably about evenly distributed throughout all the water on Earth. When you buy a can of soda, about how many molecules from that famous bathtub of Archimedes are there in that can? So what he's wanting you to do is estimate the volume of a bathtub of water, uh, basically, and then assume that's still the same rate. Assume that bottle of or excuse me, that amount of
Yeah,
water.
because I got 12 ounces yeah, I think my numbers was 12 ounces of soda. And then apparently I was looking for the volume of the bathtub that Archimedes was in. I think
Yeah,
that was my line of thinking, which I don't think that seemed right. Because I straight up requested the answer and they gave me like 200 kilograms of Archimedes
oh, that's crazy.
bath.
Yeah. So, but that's basically what you do is you calculate an estimate of the volume of.
You calculate the weight and then assume, I think it was 18 grams for a bowl of water.
Yeah, that gets you the number of moles. And then once you have number of moles, you have that number.
We have to figure out how much water could be in that can.
Yeah, because it's basically the probability is that amount of molecules divided by the total number of molecules of water on planet Earth is equal to now you're
Oh
taking.
my God. Wait, wait, God. The numbers I had to look for was how much water in the tub, how much water in the can of soda, and the total amount of water in the earth.
Right. And that's
I did not look up I did not even think about the third one, all of the water in the earth.
yeah, you got to because it's got to mix in and become, evenly distributed so that now one out of, every billion molecules that you sample from water on planet Earth will have come from his bathtub. And then you say, okay, well, what if I sample instead of, 1 milliliter, what if I sample a whole Pepsi can full of
God, I do not know how I was going to even remotely get that. I just looked it up right now. 1.386 million cubic kilometers. It's not even in weight.
yeah.
Yeah, so I don't even know. So what is kilometers, what is in ounces, and what is in kilograms?
Yeah, so they're probably saying cubic kilometers, aren't they?
Cubic kilometers, yeah.
Yeah, so that's literally a kilometer wide, a kilometer thick, and a kilometer tall cube. But yeah, so they're giving you basically in the same number of water, the same volume. They're just giving you different units to compare it to, I guess.
God. Yeah, yeah, I was not gonna get that problem at all.
Yeah,
I was
not
like,
trivial, but again, don't feel bad. Remember, I told you if it looks like your homework grades are really killing your test grades at the end of the semester, I'm going to give y'all something that I offered all of my students each semester that'll sort of
yeah,
help you
yeah,
feel.
the two cutbacks on the I think it was a cutback on two of the lowest grades in the
Yeah,
homework.
it's actually something bigger than that. But like I said, I keep that I keep that hidden until later in the semester, and then like about a couple weeks before your final exam, maybe just a week in this case, you'll hear me, and I'll say, you do this, and all will be taken care of. So it'll be.
Okay.
Don't worry. I just don't want you. When students are really go-getters and want to make their A's, they often will drop as soon as they see that there's any chance that they might not get an A. I'm trying to say, no, don't do that. This class is
It's
very
it's not meant to be easy, yeah.
it's got hard parts, but it's very very doable to get an A.
And then I didn't realize you were actually looking through the homework, so I'm gonna ask about another question that just stumped me for way too long. It's the very first question about it was calculating the mileage in Europe. It's specifically part C that really screwed me over,
I mean,
especially the answer. Yeah, it's the dollars per gallon. Yeah. What is the average cost in dollars per gallon of fuel in Europe?
yeah, gotcha.
I I saw it. It says $4.83. The answer that I kept getting for most of the math was $7.28, if I remember correctly.
Uh-huh.
My logic was essentially 6 times 1.063, because we're looking for euros per liter,
Gotcha.
and then times 1.2. Oh my God. Wait, no, yeah, 1.2, because it's 1.2 USD for 1 euro. Yeah, wait, yeah. I think that's what it was.
Yeah, this one could, I mean, if you're actually checking real conditions, this one could get screwed up, even if you did it right. Again, this is why I make up this ability to fix your homework score at the end of the semester. But yeah, this if you get too close, like this might have been made at a time when they guessed the fuel expense was $2 a gallon or something like that, and they might be expecting you to do, $4 a gallon, or you might grab $4 a gallon or something like that. But that might actually be a problem. I have to look at it more closely to see. But yeah, you basically just have to convert dollars per gallon to euros per or per liter. And did you get
Yeah,
a number that was way out in left field or what?
it was. Oh my God, did I miss gallons? Wait, did I? Because I
Did,
did. It was six. It was six. It was 6 liters per 100 kilometers, and then we do. Oh God.
hold
I
on.
think I actually. Oh God, I think I actually did screw up the math.
Yeah,
If it
six.
was six,
If you
oh,
said
six,
something, that sounds like you got.
6 liters per 100. I think it's the 100 kilometers, and forgetting about the gallons.
There's nothing. I don't even know what that is when it's saying 6 liters is some kilometers. There's no way to do a conversion between that. So I don't know what you're looking at, what you got there, but it might have been like a typo or something horrible because that number that means almost nothing. So be careful with that one. If you want,
Oh God.
I tell you what, I'll work this
Oh,
one out and post a version of it for you guys.
okay, because it, I don't know how I did not notice until now
Oh,
that
it's a
I
lot.
might have forgot about gallons.
So many things going on there. That's a very easy one to make a mistake on. I wouldn't beat yourself up about it.
Oh my God. Yeah, and then one last thing I just have to figure out. I have to reread the fundamental theorem of calculus because
Yeah,
uh
that's
something.
me making sure I say, well, I'd like to explain this and write this exactly the same, but I don't remember exactly all the terminology they use in calculus. So I'm going to just call it the fundamental theorem of calculus.
Yeah,
Don't feel too bad about not
because
knowing.
I think you were just swapping the I think you were just swapping the given equations, the
Yeah,
dv over dt, and then swapping it back to a. I just gotta remember
yeah,
the math behind it because this one, the 2t squared minus 3, and then you just go to dv over dt.
right.
That one's screwed with me.
Yeah, it'll make more sense if you can like watch the video and then like pause it
Okay, yeah.
so you can stop, think about it a little bit. That's really the best way to do it. Sometimes it just takes you. I've had times where I didn't necessarily plan to do it that way, but where I ended up memorizing, a whole long problem, and just found myself working on it so much that I'd memorized the whole problem, and then you can do it. So sometimes it just takes you literally memorizing it and thinking about it so much that you end up figuring it out at the last minute. Sometimes you don't get to the point where you ever understand it. Not
Okay,
class anyways. Uh, but
okay,
you'll get there.
got you. Yeah, I think that's it.
All right. Well, have a good one and feel free to send me a text or phone, or excuse me, email if you need me, and I'll be around. How about you, David? You got anything? I didn't even know you were here. I thought you were gone already.
No, I try to make sure I listen in on anything because if he was asking a question I might not have thought of, and I'm not up to it yet, it could definitely help me out.
Gotcha. Yeah, it's a good thing to do.
Absolutely, Professor.
Anything else I can help you with?
Not yet. I guess I'll head out now. Thank you.
All right. Thank you, David. Have a good day.
You too.